Okay, remember your paper is due Friday. I will try to remember to put a drop box out there so you can turn in your paper. I forgot. So made myself a note this time. We'll try to remember. Let's see, we've been looking a couple days at, what was it, chapter 17 on rings, integral domains, and fields. Any kind of questions from chapter 17? Well, if we start, say, looking at some of the sets we're used to working with and try to classify them as rings, integral domains, fields, there are some that are all three. What would you describe, say, what makes an integral domain special? As we start trying to decide for a certain set where it fits. What's one of the key things about an integral domain? That separates it from just any other ring.
No non-zero divisors.
Yeah, so no non-zero divisors of zero. What makes a field special? Multiplication, yeah. I mean, there's a difference between multiple and multiplication. Multiplicative inverses for everything but zero. So all but zero have multiplicative inverses. Turns out if we have a field, it has to be an integral domain. If every element has a multiplicative inverse, that there's no way there can be divisors of zero. And if we think about that a little bit, say we've got AX is equal to 0, or even just AB equals 0. If we're in a field, both A and B have an inverse. So if we multiply, say, by B inverse, AB B inverse equals 0 B inverse. B times B inverse is the identity. And A times the identity is A. What do I get on the right-hand side if I take 0 times something? We get 0. And so if AB has to be 0, if B has an inverse, A has to be 0. And the only way B wouldn't have an inverse is if it's 0. So if everything has an inverse except 0, well then we have to have an integral domain. But we do have some integral domains that aren't fields. We have some rings that are just rings. So let's begin to think about some of our standard sets. The integers. It's what we're most used to thinking with. Are the integers a ring? Yeah. We've got the two operations. They meet the conditions under addition. It is a group. So the integers are a ring. Are they an integral domain? Any way to multiply two integers and get 0 without one of them being 0? No. No. So it is an integral domain. What about a field? Does everything have a multiplicative inverse in the set we're talking about? So in the integers? No. So as we think integers, it is just a ring and integral domain. What about, say, the integers sub p where it's sub prime? So like z sub 5 or z sub 7 or z sub 11. Is that a ring? So 7-hour clock, 11-hour clock. We've used it as a group a number of times with addition. For that matter, we used it as a group with multiplication, throwing out the 0. So we do have multiplicative inverses for everything but 0. This is actually all 3. What if it's Z some composite? So not a prime, so like 12 or Z20.
They definitely would be an integral domain.
Yeah, so and why not an integral domain?
There's non-zero.
Divisors of 0. Yeah, I mean Z20, 4 and 5 multiplied to give us 0. So do a lot of other things. And since 4 and 5 multiplied to give us 0, 4 and 5 actually can't have inverses. So Z a composite is just a ring. Let's see. What about the rationals? Are the rationals a ring? Is it a group under addition? Are there any kind of divisors of 0 other than 0 itself? There's not. What about inverses? Does everything have a multiplicative inverse?
Wait, yes.
Well, in a sense, yeah, if we think about the rationals, it's some quotient, P over Q, where Q isn't 0. So what's the inverse of P over Q? Q over P. So everything does have an inverse, except for 0. I mean, 0 over 1 doesn't have an inverse, but 0 over 1 is 0. As long as, I mean, to be a rational, the denominator has to be non-zero. To have an inverse, the numerator has to be non-zero. But if you've got P over Q and neither one is 0, the inverse is Q over P. So everything has an inverse. What about the reals? Is it a ring? It's a ring. What about an integral domain? It's an integral domain. It's also a field. And then the complex numbers also is all 3. And give some fancy Q, R, and C to kind of indicate the set of complexes or reals or rationals. Now, what we're going to be doing pretty much the rest of the class is to kind of look at these examples, or these types of rings, integral domains, and fields, and begin to think, well, what kind of things are similar, what kind of things are unique to each set? Or, you know, for that matter, are there anything that's kind of unique to each particular set? So we're going to be kind of looking for similarities and differences. If we look, say, I mean, the first 3 we can kind of see. Yeah. The integers is not a field. The integers modulus some prime is a field. The integers modulus some composite is just a ring. What if we look, say, at these 2? What's the difference between the integers modulo p and the rationals? Could we find a difference between those two? How many elements are in, say, Z11?
Addition.
Well, I mean,
I guess it wouldn't matter.
yeah, just, I mean, using both addition and multiplication, because we're talking rings here, so both operations. Aren't, is there 11, 0 up to 10? What about the rationals? How many elements are there? Infinite. There's a difference. This is a finite ring, or a finite field. These are all infinite.
Can you explain what primes are finite? Sorry.
Well, z sub a specific prime, so like z sub 11. We're on an 11-hour clock. How many numbers are on the 11-hour clock?
So if your z sub a prime number, would that not just fall under z? Times a composite. I'm confused. Hold on. You saying primes and composites are different?
I mean, primes and composites are different in terms of, they're both rings, but if it's composite, we do get some divisors of 0. So they're both finite. So there's a case where there's a similarity. These are both finite, but if it's composite, it's not an integral domain and it's not a field. Whereas if it's prime, it actually is both. So there's some kind of similarities and differences, and that's what we're going to be, kind of an overall theme for the next 4 weeks is, what are the similarities and differences among our numbers? I mean, if they're all identically the same, we wouldn't need them all. So there must be some sort of differences, since we have these different sets. Can we begin to identify the different sets? And kind of focus on, what distinguishes one set from another set? And certainly one of the things that distinguishes, are we talking about something finite or something infinite? Another difference we will be looking at in a little bit, well, a few days, is what kind of equations can we solve? So for example, in the integers, say x plus 6 equals 12. Can I solve that equation? If I just have x plus some number equals some other number, can I always solve that equation? Yeah, so if it's x, just a single x. What if it's 2x? 2x plus 6 equals 12. Can I solve that?
Yes.
If I change some numbers around, will I run into problems?
As far as,
So can you think of some numbers that would give me a problem where I couldn't solve in the integers?
1/3 x plus 6.
Okay.
I guess 147 millionth plus 6.
Okay.
Because it would be
Well-
irrational.
I don't want to use 1/3 because that's not in the set I'm talking about.
Oh, I gotcha.
But that's sort of the idea. So what about 2x plus 7 equals 12? Can I solve that in the integers?
not in the set, yeah.
Not in the set. And there's a sense That's kind of why you develop the rationals. There are certain equations in the integers we'd like to solve, certain linear equations we'd like to solve, and we realize I cannot do that with the numbers I've got, because I don't have inverses. So we're going to be doing some looking at where can we solve things, where can't we solve things, in a number of these sets. Today we're going to look at kind of another property that most of these sets have in common, but a few of them do not. And that's a property known as order. Can we put numbers in order? And what would it mean to put numbers in order? So we're moving here to chapter 21. And we're going to talk about what's called an ordered integral domain. So an ordered integral domain is an integral domain A with a relation we're going to symbolize it as less than, having the following properties. Four properties we're interested in. For any A and B in the set, exactly one of the following is true. Either A is equal to B, A is less than B, or B is less than A. So any two elements you pick and you compare, you should be able to tell either that one's bigger than the other or that they're exactly the same. And if there's some way, I mean, if you can't tell, then you can't put an order, or you don't have an order. So if the way you define the relationship, if you can't tell. Now, that sounds a little strange to us, because I mean, we're used to the usual idea of less than, where yes, that's obviously true. So let me think of another relation maybe where it's not true, maybe where we try to put people in order. I mean, in a lot of sports, people are often sort of put in order. You know, you're playing tennis. You're on a tennis team. Normally they're ordered 1 through 6, but at some point during the season, you know, the 6th ranked player might challenge the 5th ranked player and beat them. If they beat them once, does that automatically they move up? Kind of depends on the coach and different things. But I mean, you could have two players that would play 5 or 6 times, and they each win once or twice. You can't necessarily know if you put two players which one's always going to win. You know, that they may be close enough to the same skill level that sometimes one wins, sometimes the other wins. So on a tennis team, it's tough to get kind of an order to know for sure. You may have somebody who's clearly number one, and a bunch that then, it just kind of depends on the day how they're going to be. So for our order, we don't want any of that uncertainty. We want to know, if we compare two numbers, which one's bigger. And then for the next 3 properties, it's for any A, B, and C in the set. If A is less than B and B is less than C, then A is less than C. Transitive property. If A is less than B, then A plus C is less than B plus C. Add the same thing to both sides. We don't change the order. And this last one, if A is less than B, then AC is less than BC when C is greater than 0. So if we multiply both sides by the same positive number, the direction of the inequality stays the same. Now, if we look at this, all of this seems fairly standard. The reason it seems fairly standard is the integers is an ordered integral domain. The rationals is an ordered integral domain. The reals is an ordered integral domain. So the numbers we're used to working with most of the time are an ordered integral domain. They have all these properties. So let's talk about two other integral domains I had on my list that we're not as familiar with. So say, let's work with Z sub 11. Suppose you may look at Z sub 11 and think, oh, 10's bigger than 9, is bigger than 8, is bigger than 7. The problem comes with properties 3 and 4. If we use our usual notion of order and say, well, 6 is less than 7. What if I add 4 to each side? Doesn't change? 10, on 11-hour clock, what is 7 plus 4? Yeah, we're on an 11-hour clock. And that's one of our challenges when we look at something new. It's like, oh yeah, it's not my normal addition. In this case, it's that, so we get that 10 is less than 0. Well, the order we're thinking, 10's not less than 0. And we could struggle and try to come up with some other order. No matter what order we come up with, there's going to be this problem that we can't get things in order. We'd also have the problem, if we multiply by something greater than 0, so say here, 6 less than 7. What if I multiply both sides by 5? I think 5 will do it for me. 5 times 6 on our 11-hour clock is 8. 5 times 7 is 2. That's a problem. So we have some issues here with adding the same thing to both sides, multiplying the same positive number to both sides, in terms of trying to put together an order for Z11. And we'd have the same thing for any prime. So there's no way to put an order on the clock. And if you kind of think about that, I mean, the fact that we go around and around and around, who's to say that 6 is less than 7? Because we might have gotten even to 6 by going around once So we actually traveled longer to get to 6 than we did to get to 7. So it's just there's really no way with Z11 to make this, to put any kind of order on it.
Is there a way to make it happen for any closed cycle?
I don't think so. We'd have that problem really on, any kind of closed cycle.
So is it truly doesn't work, or like we can't show that it does work? Because we can't explain.
Well, it doesn't fit the properties. When we start with an order that we think makes sense, it doesn't satisfy all the properties to be called an order on that set. And even if we tried some other sort of order on it,
Just can't be bounded.
because I think, I don't know that we'll get into this, but I think if there is an order, you've got sort of 0, you've got your positives that are bigger than 0, and your negatives that are less than 0. And a number and its additive inverse have to be on opposite sides. I think that's a property that can be proven from what we've got here. If we look at an element and its additive inverse, they have to be on opposite sides of 0. And on a finite set, it's a lot harder to see, well, how did 0 kind of divide this? Another set that we have issues with would be the complex numbers. Here, rather than thinking sort of a specific idea of how we'd have it ordered, I'm going to focus on one complex number, I. Do we want to call I mean, if we compare it to any other number, exactly one of these three has to be true. So let's compare I and 0. Do you think I is equal to 0? No. I mean, as we look at it, in terms of equal, no, I and 0, I mean 0 is the additive identity, I is not, I and 0 don't look to be the same. So, this one's out. I is 0. So the question is, well, is I positive or is I negative? Well, if I is positive, I can multiply I to both sides. And if I multiply by a positive number, the direction of the inequality stays the same. I times I then would be greater than I times 0. So I squared would be greater than 0. But what's I squared? Negative 1. Yeah, and negative 1 it isn't bigger than 0. At least not with the order we're used to working with. Okay, so could I be negative? Well, what happens if I is negative? I multiply both sides by I. we could prove that if you multiply by something that's less than 0, the direction of the inequality is going to reverse. So I squared again turns out to be greater than 0, and that's a problem. So there's really no way to order the complexes. I mean, another place where we kind of see this idea where there's some things where it's tough to order. I know I've got a few football players in here. The NFL draft's coming up. All kinds of mock drafts of what order are people going to be picked in. Do they agree? No, because everybody has a different idea of what they think the team needs, and even a different idea of what are the best prospects out there. No. So the teams have done a lot of work trying to see, but there's no nice order that you can look at and say, this player is clearly better than this player. Now, there are some players. Okay, this player is clearly better than this player. But there's some at every level where people are looking at, and I know on one person's draft board, they have somebody rated above and somebody else not. And that's the challenge to try to kind of, as they're looking to figure out, will the player I want still be there when it comes my time to pick, or do I need to try to trade up to get the player that our organization really wants, because somebody that's got a choice ahead of us, we think they're going to take them. And we want them enough that we're going to trade up. So there are lots of things that are kind of thought about there, because there's not any nice order that everybody agrees on. That of these 10, we know exactly which one's the number 1 prospect, and everybody wants the number 1 prospect, and so nobody's going to trade you because they want the number 1 prospect. No, that doesn't happen in any kind of draft situation. Now, on the playground, it can happen that somebody is the number 1 prospect whenever, however you grade up. Somebody is always, the same person is always picked number 1, or last, as the case may be. You never know how those things work out. But I mean, there are situations where there are clear sort of number 1, number 2, but after that it gets a little bit more complicated. So I can see some of you thinking, I was always the number 1 when picked. It's like, me, I was on the other end of the spectrum usually. It's like, so not everything can be nicely ordered. Turns out we actually want to take this one step further than beyond just order. We want to talk about what's known as a well-ordered integral domain. So not just having an order we can put on it, but what's called well-ordered, which means is an ordered integral domain. So we have to have an order in the first place. Where any non-empty subset has a least element. So we've got an integral domain. There's an order on the integral domain. And the question is, if we pick a subset, any subset, can we always figure out the least element? So let's look at a few examples. Say the set of x greater than or equal to 1/2. And let's think of this on the reals. So all the reals. is their smallest element in that set, or at least element in that set?
Yes.
What is it?
1/2.
1/2. Similarly on the rationals. What if we're talking integers? Is their least element? One. I mean, we described it a little weird if we're talking only integers, but 1 is the least element. What if I change this to x greater than 1/2? On the reals, is there a real number that is the smallest real number that's still bigger than 1/2?
Yes, but it's infinitely close to 1/2, I don't know.
Okay. Let's talk rationals first, and then we'll, although I guess rationals we have the same issue, right? Although rationals we have a little bit better way to describe that idea. So say, what, 1 million over 2 million in 1? Nope, not 2 million in 1, 1,999,999. That's a little bit bigger than 1/2. But is it the smallest element in the set of rational numbers bigger than 1/2? Because we could go to 1 billion over 1 billion over 1,999,999,999.
Yeah.
So there's that idea. We can get as close to 1/2 as we'd like, but no matter how close we are, we can always get closer. So in both the rationals and the reals, there is no smallest element. So they are not well-ordered integral domains.
Is it a well-ordered set if we only look at the integers, if it was x less than or equal to 1/2?
Okay, yeah, I just realized looking at my notes here, I had missing an important part of this definition. Where any non-empty subset of positive elements has a least element. Because you're right, if we look at x less than 1, the integers would have a problem. But if we're looking at some positive integers, a positive set. So here, changing this to x greater than 1/2 doesn't change the fact that 1 is the least positive integer in that set. And it certainly doesn't have to be just 1. We could look at the set of, say, the set of x bigger than, how about bigger than pi? In the in the integers. Again, it's a little weird way to perhaps describe that, but in the integers, is there a smallest element in that set? The least element?
Yeah.
And it's 4. In fact, probably rather than using that description, if we were talking integers, we would start with the smallest element and work our way up. But there would be a smallest element. And normally if we write a set of positive integers, then that's the way we'd write it. We would start with the smallest element, kind of demonstrate the pattern, and work our way up. So even things like multiples of 3, greater than 100. So, integer multiples of 3 greater than 100. Is their smallest element?
Yeah,
Okay, can we, what would it be?
102.
102. And then what, 105, 108. So it turns out the integers is the only well-ordered integral domain. Up to isomorphism. If you had another one that was well-ordered, you could just map 1 to whatever the smallest element in that integral domain. And notice in this case, what 1 not only has the special characteristic that it's the smallest integer in lots of sets, and we can't get any positive integer smaller than 1. 1 is also the multiplicative identity. And it turns out if we've got a well-ordered integral domain, whatever the multiplicative identity is, that's what's going to have to be the smallest element. There's no way to kind of squeeze anything between 0 and your multiplicative identity. Building off this concept, we get an extremely powerful technique of proof known as the principle of mathematical induction, which you've probably seen in other classes, and we're going to spend a day or two kind of working with it here as well, because it's so important. Just to make sure you've seen it and work with it. So today we'll talk, I'll state the principle of mathematical induction, and we'll, Wednesday, come back and do some examples. So, a statement P sub n is true for all positive integers n provided two things happen. Actually, let me call it S sub n, because I think that's the notation the book uses. Provided S sub 1 is true. And then the second property, for any positive integer k where S sub k is true, S sub k plus 1 is also true. And if we can show both of these, that is proving our original statement is true for all positive integers n. And this, proving it by what's called the principle of mathematical induction, or just proving it by mathematical induction. Let me see if I can relate it back to well-ordered just a little bit. So we've got a set that's well-ordered. I mean, the integers is well-ordered. So suppose we've got this statement S sub n, and suppose it was not true somewhere. If we look at the set of places it's not true, that set has the smallest element. If it's not true at 1, well then, okay, the principle of mathematical induction would fail. It's not true at 1. But suppose it's not true at 4. Well, if it's not true at 4, then it was true at 3. But if what we've got here is correct, if it was true at 3, well, then it would have to be true at 4, and you get a contradiction. So if this is true, then the only place the original statement could be false is where it starts, because if it's false anywhere else, and this is true, you get a contradiction. I mean, another way of maybe thinking about this, how do you climb an infinitely tall ladder? You have to get on the ladder, and then once you're on the ladder, you have to take the next step. And from the next step, you can take the next step, the next step, and the next step, et cetera, et cetera, et cetera. And so, in a sense, this part is sort of the et cetera argument we might like to make. It's just mathematically, we use mathematical induction rather than saying, you know, well, this will keep working. So if you're on a step and can always take the next step, and you can actually get on the ladder, then it's true for all positive integers. And this is modified a few times in that we wouldn't necessarily have to start at 1. And it can be true then from wherever we start on with that. Yes?
Does that mean SK minus 1 is also true? So like if we were at 4 and it was true at 4, would that mean 3 would have to be true in order for us to get
Well,
to 4?
I mean, we typically tend to move forward with this. I think if we can move forward, I'm trying to think if we can move backward. I mean, typically we are trying to move forward. So we start, and so if we look at this, if S1 is true, so S1 is true, if we can prove that, then well, S2 has to be true. Then 2 is true, so 3 has to be true, 3 is 4, 4 is 5. But we do this much more in general. We don't look at, well, 2 implies 3, 3 implies 4. We look at it as S sub k implies S sub k plus 1, and that works regardless of what step we're at. If we can prove that somehow we've ended up at a step where it's true, and we can conclude, okay, at the next integer it's also true, that, along with the fact that there's a place we can start, means the statement is true for all positive integers from wherever we happen to have started. And for this form of the principle of mathematical induction, we're starting right at 1, the smallest integer. There are other forms where we could start, maybe at 2, and so prove it's true from 2 on, or start at 4 and go from 4 on. There's some other forms where we change this slightly, so there's some variations on this form. Next time we'll look at some specific examples of, okay, well, how do we actually apply this? Some of which you've probably seen, some of which maybe will look a little different with that. So I will see you Wednesday, and I will try to get the Dropbox out there